Hello everyone, welcome back to another DDLC seminar. Today we have the honor to have Professor Alexandre Bayen. Alexander Bayen is the founding associate provost for the Berkeley Space Center, the director of the Center for Information Technology Research in the Interest of Society, and the Banatao Institute, and the Liao Tso Professor of Engineering at UC Berkeley. He is a professor of electrical engineering and computer science and civil environmental engineering. From 2014 to 2021, he served as the director of the Institute of Transportation Studies at UC Berkeley. He is also a faculty scientist in mechanical engineering at the Lawrence Berkeley National Laboratory. He received the engineering degree in applied mathematics from the École Polytechnique France in 1998, the MS and PhD in aeronautics and astronautics from Stanford University in 1999 and 2004, respectively. He was a visiting researcher at the NASA Ames Research Center from 2000 to 2003. Between January 2004 and December 2004, he worked as the research director of the Autonomous Navigation Laboratory at the Laboratoire de Recherche Balistique et Aérodynamique, Ministère de la Défense, Vernon, France, where he holds the rank of major. He has been on the faculty at UC Berkeley since 2005. Bayen has authored 2 books and over 200 articles in peer-reviewed journals and conferences. He is the recipient of the Ballhaus Award from Stanford University, 2004, of the Career Award from the National Science Foundation, 2009, and he is a NASA Top 10 Innovators on Water Sustainability. His projects, Mobile Sensory and Mobile Millennium, received the award for Best Innovative Practice at the ITS World Congress. Mobile Millennium has been featured more than 200 times in the media, including TV channels and radio stations, CBS, NBC, and many more. And in the popular press, Wall Street Journal, Washington Post, LA Times, and more. Bayen is the recipient of the Presidential Early Career Award for Scientists and Engineers Award from the White House in 2010. He is also the recipient of the Okava Research Grant Award, the Ruberty Prize from the IEEE, and the Huber Prize from the ASCE. Professor Alexander Bayen, welcome.
Thank you so much for the very generous introduction. I'm really excited to be here. Greetings, Andreas. Let me just share my screen. Give me 1 second, and I will be able to share my slides. Okay. Okay, so today I'm going to talk a little bit about mixed autonomy at scale. I don't know if, do you see my slides okay?
Perfect.
Okay, wonderful. Perfect. Thank you. So thank you again for the generous introduction. I'm really excited to be here. I'm going to talk a little bit about mixed autonomy at scale, but I'm going to start from a long time ago journey, which is kind of a back to the future return that the new revolution in AI has really enabled in the recent month. So back in the days when I was a PhD student, I used to work on air traffic control, which is what this movie displays. This movie is probably almost 30 years old now. And this, at the time, I don't know if you see well with the granularity in time, but this is an example of air traffic over the United States. At the time, I think we had up to 5,000 aircraft at a given time, 17 transcontinental flights a day. And I think the game there was to understand how to do multi-agent control over these very complicated networks, given that there is a human in the loop. And more specifically, some of the difficulties at the time arose in the arrival airspace because of the need to sequence aircraft into the runway. And so the job that I had as a PhD student at NASA Ames at the time, when I was a PhD at Stanford, was to understand how we could use the modern frameworks of the time, which at the time were hybrid systems, so almost a precursor to CPS systems for that. And the paradigm, so we're talking late 90s, was essentially that we're going to use the FAA architecture to essentially devise, lay on top of it, set of controllers that can be compatible with the framework. And the framework at the time had humans in the loop, just like today, it still has humans in the loop. So there's a command center which issues very high level directives, and then centers manage multiple sectors, and then sectors work within a given framework and then deliver aircraft to the descent and arrival airspace. And so the framework at the time was interesting because in some ways it was already driven by language, but language meant at the same time humans, and at the same time what we thought was a good modeling framework at the time, which is the framework of hybrid systems. So for example, if you told at a time to an aircraft to hold, it would somehow be a pattern where they would fly in these loops, which I'm sure many of you have experienced upon arrival if there is too much traffic on the runway. If the delay required for maintaining capacity was smaller, say you want the aircraft to be delayed by a minute or two, then you would do something called the vector for spacing. And so on and so forth. And so the idea is that when humans talk with air traffic pilots, these things are conceptually easy for pilots to do, and they're easy for humans to verbalize over the radio. And you can see that this is way before LLMs. This is way before even NLP was anywhere close to be able to transcribe this automatically in a way that could enable automation. But the mathematical frameworks for this was already the center of a lot of interest to the community. And so the idea was that you could essentially work on the genesis of controllers that would jump between these different modes. And if you summarize the job of an air traffic controller at the time, it's really a way to communicate with the pilot, is like switch from this mode to that mode. And then the pilot has a mental model and knows how to do that, which in turn gave rise to a lot of interesting dynamical systems models or hybrid systems models to model aircraft, with the notion that maybe one day an optimization paradigm over hybrid systems could enable this system to work better, and ultimately for this system to be decentralized, or what was called free flight. And from a controls perspective, in some ways, it's really thinking, okay, so I have a bunch of hybrid systems flying around, and what I'm trying to do as kind of a management of the system, centralized or decentralized, is to build a controller on top of it. So for example, in the very final arrival of the airspace, the idea is that you could fly direct to a destination point, and depending on your descent speed, that will give you a range at which you can land. And then if you're delayed on the way because you take one loop around that point, which is a possible place where you can hold, well, you have another landing strip. And so the third, if you do two loops or two sequential loops, then etc. And then like this, you build these kind of landing maps, and you can see where I'm going with this. It's almost like a feasible set of a mixed integer linear program where you're trying to sequence aircraft across non-convex landing strips, which enable the aircraft to be sequenced and separated on the runway. So you can see how with this, you can essentially achieve high-level planning in a way that is compatible with something that maybe one day will be verbalizable automatically. At the time it wasn't, but at least would enable the pilots to work with a traffic controller by being compliant over what was happening over the radio channel, and yet be able to automate that, or at least execute these if they were not flying automated aircraft. And then, of course, at the lower level, you wanted to also ensure that there's no collision. So there was a lot of very active work in the Hamilton-Jacobi space, where essentially you would model aircraft as hostile to each other, where one is trying to crash the other, because if one is trying to crash the other and you have a controller that always escapes, that's kind of a suicidal attempt. In some ways, it's a version of robustness where no matter what the opponent does, you have a way to escape. And that gave the rise to a lot of the very common today Hamilton-Jacobi framework, which originates with the work of Shankar Sastry and Claire Tomlin in the mid-90s, and then that the next generation, my generation, took over as PhD student until the advent of numerical analysis enabled the computation of these solutions in maybe 3 or 4 dimensions. And at the time, we tried that on specific air traffic control routes. This is an example of flights at the border of California and Colorado and Arizona, to see if there would be an opportunity for this to run onboard the aircraft, ultimately giving rise to a possibility of a little bit less supervision of the human from the ground and a little bit more decentralization of air traffic. Some of the students in the group, in particular Rodney Teo, even went as far as implementing this on drones. This is an example of an algorithms that I described earlier that ran early 2000 at NASA Ames on some of the drones that at the time the students had to manufacture themselves. You couldn't just go and buy things. You just had to build these things, which is why they look so old. But it showed that at least the commands that we issued in the simulations could one day be implemented in automation. So at the time, I think in the early 2000 or late 90s, it was really exciting because people really thought that this would be a next generation air traffic control that might happen in the en route airspace. And then this happened. September 11th. This is an example of well, this is what happened. This is the all the aircraft in the United States landing right after the attack in New York, and you can see this is probably the only time in the recent history of the U.S. that the skies were so clear for so long following these attacks. Of course, September 11th drastically changed the approach. And in some ways, I think the research in air traffic control automation or human supervision or mixed autonomy really took a dip, maybe 1 or 2 decades dip, which never really recovered at the en route level or even the arrival level. And it might have happened anyway, but I think certainly we saw a major shift in the way things happened at NASA at the time and even at the FAA just because of the new reality of geopolitics. So at that time, this is when I decided to switch my research to something which brings us closer to what I'm going to talk about today, even though at the end you'll see they all converge. This was the time at which cell phones started to rise. And so now we're in the early 2000s or mid 2000s, and it's the rise of the IoT. And so suddenly there is a huge surge of information which was not there before. I mean, in air traffic control, you work with a lot of good information because radar is pretty good. But anywhere else, for ground transportation, information was very poor, very sparse, until phones came along and people thought that you could use the GPS on board the first generation smartphones to monitor traffic and provide information of traffic at global scale. And so this project, which essentially took place at the time we were winding down on the air traffic work, was the first traffic app that was ever deployed in North America to enable traffic information systems to lay real-time information from smartphones collected by these things. So this is a E71. That was at the time the latest smartphone in the Nokia brand. iPhone 1 did not have a GPS at the time, and there was no Android. Android came a few years later. So we built this first system and we deployed it in North America on RIM phones and Nokia phones. And over the course of 2 years, it enabled us to produce what you see on the right, which of course everybody here has now on their phones for free everywhere all the time. But at the time, you have to recognize that in 2008, if you were looking for traffic information, the screenshot of the website is really what you would do. You'd go to desktop, you would just click, you would look at the route which has congestion, and then you would just hope that things stay that way. We were very excited about that project because it was the first opportunity for us to do a lot of data assimilation at scale with partial differential equations where you have Lagrangian measurements, which are essentially measurements along the phenomenon you're monitoring. And so along that same token, because we were really interested in Lagrangian monitoring and still in the context of these multi-agent systems, we also were interested in water monitoring, which is not that different from, in some ways, the traffic monitoring. You have some form of stream, and the stream pushes the little floaters, and then the floaters can monitor, they can move eventually to monitor things where you want them. They can radio it back. In fact, these were the first time that we put floating phones. Each of them has a phone inside. And then the same algorithms in the background enabled us to essentially reconstruct the traffic in real time. So what you see here is some deployments of these sensors from our boats. And then you can see some aerial view of what they are. And you can see particles that are modeled by the either shallow water equations or very easy equations, very easy versions of Navier-Stokes 3D with real-time data being streamed in by this. And this is important because I think today in automation of the large-scale systems we're interested in, there is a closed loop where the monitoring is now possible. This was not possible for sure 20 years ago. So this was the first attempts to do this with traffic, like I showed, with water. Then we also did that with earthquakes. And so this is here another interesting thing. As you remember, iPhone 2 had accelerometers in it. And so we were the first app that monitored earthquakes by using the accelerometer data from the phones. And then what you see here is a shake table. So these are usually built to shake big things you built out of concrete to test their resistance. But here, what we wanted to demonstrate at the time is the ability of a very low quality accelerometer to capture accurately an earthquake, which has a pretty low bandwidth. Obviously, these are slow variations. And again, with the same idea is that with the rise of the IoT and Web 2.0, it would become more and more possible for large-scale infrastructure systems to stream data or natural phenomenon to be captured by these, and the phones was one of the many vectors that was possible. And so that led us to the idea of large-scale control of networks. So since we couldn't really do it in the air because the paradigm had been frozen after September 11th, we decided maybe some of the same techniques could be used on the ground. And so at that time now, smartphones were rising and data became available, or at least if you're working in infrastructure systems, this is an example of data we collected from the 500 taxi cab in San Francisco. Just to give you a sense, this is now, say, mid 2010, so 2008, 9, 10, 11, 12. Today, there's 40,000 registered Uber drivers just for San Francisco. So it's like the scales, even between then and now, or like logarithmically at least one or two above. But I'm showing this because this is how in some ways the infrastructure came online. And at that time, we had probably written over a dozen papers on data assimilation. So how you take these mobile measurements and you include them into live traffic maps to operate the infrastructure. So that enabled us to start thinking about how you build such a system. And for example, for the geography we were interested at the time, so again, about 2010, typically for a corridor in LA, like the 210 corridor you see here, which spans a few suburbs of LA, you'd have something like 500 control points. Okay, so that means essentially there's 500 traffic lights you can probably integrate into a single decision support system and use that data to improve some of the metrics you're interested in. Some of the metrics might be travel time, might be total vehicles traveled, might be VMT, might be CO2. There's different metrics. They're not all aligned. But the idea is that we were interested at the time to put these infrastructure online. And so we were doing this also in light of traffic information. And the idea there is that if you have an accident, but in one case, 20% of the people have a smartphone and follow their smartphones, traffic will behave a certain way. That's what you see above. And if they don't have that information, traffic will behave a different way. And that's what you see below. And paradoxically, and as many people discovered in the 2010th, the more information you give to people, sometimes the more problems you can create because everybody gets the same information at the same time. And there's some very classical economics theory which shows that then people will all choose the same route. And because of that, instead of creating a social optimum, you'll create something which is closer to a Nash equilibrium. And then there's a price of anarchy. And the way it materializes itself is that it increases the level of congestion when in fact, if people had not been given the information, paradoxically, things might have been better. So at that time, the whole ecosystem of control theory was discovering this paradox in practice. This paradox has been known since for a very long time. I mean, I think the PhD of John Nash is in the 50s, the Nobel Prize was in the 90s. But it was the first time that things became to grow at scale so much that people could experience it. And so these are things we were interested at the time in terms of the multi-agent controls that we were using for the traffic light coordination system, and possibly the idea that we could one day coordinate the information in the way it's conveyed to people with the infrastructure management. And in some ways, it took 15 years for this to happen. So we realized that problem in 2010. And finally, we have a paper coming out in a few weeks with a major traffic information company. So smartphone, I can't tell the company because the paper is not out. It's going to come out in Nature. But this is the first time that this type of paradox was realized and implemented in an actual smartphone app to provide routing guidance that is not going to lead as much to a Nash equilibrium as you could. And so this is another interesting thing because the reason it took 15 years is that the interface between what's happening at the infrastructure level and what's happening in the private sector level for these guidance system is jurisdictionally very secluded. So fast forward now 5 years, we see cars coming up with some levels of automation. So say the late 2010s is glorified cruise control systems, then adaptive cruise control systems, then maybe one day cooperative cruise control systems. And then some companies like Tesla was one of the early ones starting to suddenly rise the level of automation from 1 to maybe aspirationally 5, which we of course see now, or close to 5 with Waymo. And so that rose another question, which was even more interesting, is that if the routing guidance, which I talked about, which essentially tells you which route to choose from A to B, is now linked to some form of control guidance, can you use that to improve traffic? And improving congestion is a very specific problem. It's like matching demand and supply in the network, and that happens by routing. So once the vehicles are on the road, that you can change. So in some ways now demand is realized, but you can still improve traffic, not so much the VMT or total vehicles traveled, but with whatever you've got on the road, the efficiency of traffic can be improved by changing the traffic patterns. And that's when we became interested. So now we're talking 2013, 14, 15, in understanding how low levels of automation in some vehicles could lead to some interesting improvements in the local traffic features. So for the next 20 minutes here, I'm going to use a color code where in red we have some vehicles with some level of automation. So not fully automated. Think of, whatever car you can buy where there's some form of autopilot which will wake you up if they need you, and otherwise will probably take care of you. And then they interact with other vehicles, like my vehicle has absolutely no automation that I drive myself, and therefore have a specific behavior, which is the behavior of the humans driving it. And there, the idea is that the V2V paradigm is not there yet, and it's going to be probably a decade and a half before it's there. But with very crappy systems for transmission, such as the cell phone system, very unreliable, very low bandwidth sometimes, very high latency sometimes because of coverage, you could still transmit information kind of like in the old air traffic control world before, like very high level, but you cannot transmit reliably high bandwidth information, which is an interesting control problem now, because essentially you could possibly use this to do high level coordination of vehicles, hoping that you can develop a low level controller that can control it. And with that, do what we used to do with air traffic control is like if you give some information to specific vehicles that have a distributed capability to control the entire traffic flow, you possibly could improve things on the ground. So we became interested in building a system where, so this is the beginning of cloud now. So we're talking 2014, 15, 16, 17, where running things on old stacks of computers was becoming obsolete, and the cloud could support much faster paradigms. And the idea was to have a very fast computational framework on the cloud, transmit very high-level guidance to vehicles, so low bandwidth, high latency, and then the vehicles run a local controller that could absorb this information to improve traffic. So we called it circles at the time, and it was really the emergence of what became known later as mixed autonomy traffic, which is still a field of great activity, both in air traffic, there's a rebirth, and of course on the ground. And so in the color code I'm going to use for the rest of the talk here is essentially a paradigm by which we will depict in red vehicles which have a specific level of automation. And it can sense some vehicles in blue that are either in front or in the back, or some information is giving them. And then there's white vehicles that are there, but there's no knowledge of the red vehicle that there's a white vehicle. They might observe the effect indirectly, but they have no way to sense anything about that vehicle. And so now it's about 2016, 2017, and we realize, okay, so deep reinforcement learning probably has an ability for us to come up with policies learned through black box simulation. So take a very accurate simulation, like maybe not as good as Carla or something like this at the time, but like a micro simulation tool with very good models of humans, and see if one could devise a policy that can be used for control. And so it's interesting historically too, because now we are going into maybe 2020, 21, and suddenly it has become possible to do deep reinforcement learning over micro simulation tools. Microsimulation is an approach which is a classical approach in transportation engineering. It's over 20 or 25 years old, but for a while you needed gigantic computers and to run these models, because you have one trajectory for every vehicle, and you did huge amounts of data to calibrate these models. So when I started at Berkeley working on air traffic control, that data and that compute was not there. When we started working on this integration in the late 2010s, so 1918, maybe 20, not only was the compute power there with the advent of AWS, but also the data I've shown was enormous. And so now there was enough data to do simulations that you could have maybe 50,000 vehicles in a simulation and then run them in batches to teach an algorithm how to devise a policy. So in 2017, we were the first group to integrate these three things on the cloud. So the cloud was the platform now. RL libraries were coming out of the lab, very fresh and open source. And traffic simulators were tractable in the compute environment we had. So we built that platform. We called it Flow. In fact, Imsun, which is now owned by Siemens, rolled out their first cloud version for us. We were the first implementation in the history of the company. And of course, at the time, Sumo was an open source framework we could use as well. And that's the platform we use to train our policies. And so this is an opportunity to maybe do a little bit of a leapfrog back in the model-based research world, because traffic models have been around since the 30s. This is a picture of Bruce Greenshield, who built the first aggregate model of congestion, or at least to our knowledge. Took 20 years for the PD community to notice and integrate this in hyperbolic first-order conservation laws. And it took another couple of decades before people started to thinking about instabilities in these things. This is a very famous movie by an experiment run by Sugiyama in 2009, in which you're asking people to drive around and keep their distances. And this movie is very famous because you can see within 30 seconds, humans are very incapable of such a thing because they tend to amplify instabilities rather than damping them. It's kind of a natural tendency to catch up with the person in the front. And so fast forward this another 10 years, this group of amazing people, Work, Piccoli, Siebold, and Sprinkle, and Maria Laura de la Monache created this experiment in which they inserted a car, which you see with the arrow inside these instabilities. Right now, the car is driven by a human, so that's why even the human is not able to do well on all the cars. But now they turned on a very simple algorithm called the follower stopper, which enabled that single car to stabilize the entire ring. That was pivotal because, to my knowledge, that's the first time stabilization effort in mixed autonomy setting is done in a setting like this that enables to show savings of up to 40% of energy. And that's not a model. They actually measured the gas and the fuel consumption. And so this was eye-opening for us because suddenly we could see the convergence of deep reinforcement learning with field operational testing at a time when stacks in vehicles could enable such things to work at scale. And so this enabled us to rethink the agenda. 1 year later, Kathy Wu, who is now a professor at MIT, redid the same experiment in simulation, which is what I'm showing you. So right now there's the instability. And once the red car crosses the line, what you will see is that it will stabilize these instabilities. So you might wonder, well, why did Kathy Wu did an experiment in 2018 when they did an experiment the year before? And the reason is that the follower stopper that they used is an expert controller. This is a policy learned in black box deep reinforcement learning, which essentially spits out a action on the basis of a reward and an input state, which means that essentially this policy bypasses any model of traffic ever deployed since 1935, which is somewhat crazy because if you think of the literature, there's tens of thousands or thousands of articles written on that topic, but somehow now it's 2020 and deep reinforcement learning enables to bypass all that research, which it doesn't mean it should be thrown in the garbage, but it means that there is another approach which might be equally interesting for experimental purposes. So we tried that on a variety of settings at the time. For example, you can generalize this setting to a two-lane ring. And so it's interesting because here the policy discovers that by switching lanes obnoxiously, like I'm showing now, you can stabilize two rings by disabling people to pass you and forcing the speed on them. Obviously, it's black box deep reinforcement learning. So I'm just verbalizing something which the PPO we used at the time discovered by itself. And you could say, well, that's pretty intuitive because in some ways that's what a snail operation does, right? A snail operation is something used by the police when you reopen an asset like a bridge. You don't want people to go 150 miles an hour, so you kind of limit the speed up front. So you could see maybe the deep reinforcement learning had some form of human behavior or emergent behavior it captured in the optimization, but it was certainly not by design at the time. Other things we were experimenting on is things like this, which is the worst possible way to manage an intersection. You put a stop signs, which maximizes both travel time and emissions of CO2. But if you make sure the algorithms has vision over all the vehicles, it actually learns the proper speed at which it should travel. So the intervehicular distance makes the length of that snake into half of the 8 figures. So it's kind of interesting that, again, it figured this out. Which is another way to say that it rediscovered platooning if you plot this in a time-space diagrams for people who have taken a transportation engineering class and used that framework. I'm going to skip a bunch of different things, but other things we were trying to do is transfer learning. It's like, can you learn a driving policy on a ring and implement it in real life? So the idea is that here you want to test things where waves are generated at intersections. So when there's an intersection, it creates a back propagating shock wave. And when that back propagating shock wave happens, then this is when the energy inefficiency happens. And so here, what we wanted to do is we wanted to show that if we insert these self-driving vehicles in that mix, could that smooth traffic and could that essentially fix the problem? And so this is what you see here now. Every once in a while, there's a red car, and the red car, so initially not much difference, but as we inject more cars into the on-ramp, you'll see the waves propagating backwards. You can see that one is forming right now. And if I keep doing this, there's going to be more waves. And here, look, the left, the car has stopped. So it's figured out that if it stops and then reaccelerates, it will actually be more energy efficient for everything. So you've essentially taught a self-driving vehicle to be a traffic light. And here's another one stopping again. And you can still rationalize this, right? Because if you look at the time-space diagram, you see that every time you merge a car, it creates this back propagating shock wave. And then so if you have knowledge of that shock wave, the car figures out that it should slow down, because if it slows down early, then essentially by the time it reaches the merge point, there is no more wave. So in some ways, it has enabled all these vehicles behind it to not stop and go. And so the savings are quite substantial. So this was picked up by the news at the time and even by Science Magazine, which enabled us to really talk with sponsors, and in particular the US Department of Energy and three car companies, about possible experiments we could run at scale. And it seemed at the time that the right focus for us would be these jammetons or phantom waves or stop and go waves, which many of you have experienced. It's a case like this where there is no congestion that is visible because actually the demand is below the supply, right? But for this reason I showed before, where humans are pretty inefficient, that traffic at critical mass creates these stop and go waves, which are essentially the cause of inefficiency. So here we're not trying to fix traffic in fixing this. We're trying to fix human efficiency with automation, which is a very different problem. We're not going to change the number of people going onto the freeway. That's not our ability, but we have the ability to change their behavior once they're on the freeway. So to tackle that problem, we first thought that we would use the setting I showed you earlier in 210 in Southern California. And so we started building these gigantic models. And so it's going to be hard to see over Zoom because there's a bit of a stroboscopic effect given the frequency and it's an accelerated movie. But what you should see if you see my mouse, is there is a pocket of shock wave that is forming on the right, and it's progressively back propagating into the box. Now it's entering the box, and if you look in the box, suddenly traffic gets much slower, and then you have these oscillations back and forth. There's a bunch of red cars, but right now the red cars are not turning on the controller. And then in about 15 seconds, you're going to see blue cars appear. And when that happens, that means the red controllers have turned on the policy they learned in black box simulation. So here the notion was, why don't we use a fully calibrated micro simulation model that we happen to build for District 7 at Caltrans? And why don't we use that to devise a policy that would run on these? See, it happened now. The cars turn blue. So now visually, I don't know if you can see this over Zoom, but things are much smoother. The total number of cars flowing in and flowing out does not change. We don't change the supply demand inbound and outbound ratios, but the flow has way less variance in speed, which is what this mixed autonomy work we were doing is trying to achieve. So that was the work at the time, and so then we went to talk to a few agencies and demonstrated that we could run this in hardware. So the idea was to do transfer learning from pure simulation to hardware. So this is far from being the I-210 in Los Angeles. This is the last NSF CPS meeting before COVID. You can see Eugene Vinitsky on the left and Fengyu Wu on the right. And this was a way to demonstrate to the NSF that we can run this in the hardware. And of course, this is hi, Andreas. This is your stuff. Back in the days at University of Delaware, and I know you have a much better version here in Cornell. This was another example we ran together with Andreas's group to show that we could transfer. This was a sequencing policy. You can see on the right. We control the vehicles in a way that the last vehicle leaving the roundabout, which is the Hummer on the right, leaves before on the left, which is the baseline policy. So showing that this sequencing policy we had learned in black box deep reinforcement learning could be rolled out from the simulation to the hardware. And this experiment that we did thanks to Andreas's group at Delaware, so the Gen 1 simulation city, was essential in us going to the DOE and say, look, okay, we've pushed it as far as we can in the field of hardware. We're now ready for real-time deployment. And Kathy, in the meantime, has joined the Waymo, and so it's a nice continuity also in terms of the industry and where students work. So going back to the experiment of 2016, this convinced us that we're ready for larger experiments. I'm going to skip the 2018 experiment that was run by the Vanderbilt team. And essentially then came 2021, kind of the middle of COVID, we decided to do a 10-car experiment in which we could essentially control things on a single lane of freeway at scale. So we chose a stretch of road close to Nashville and Smyrna, about a 5-mile stretch of actual deployment. And essentially proceeded in some form of funeral style. So putting all the vehicles on the freeway in a sequence and then letting them operate on the freeway without controlling people, which essentially means you have, for the experiment, we ran 4 actuated vehicles in red, some extra vehicles in blue we had inserted just for monitoring the experiment, but not controlling, and then a bunch of people in between that come in, come out, and merge into your lane. And what we noticed, so we managed to catch usually 1, 2, sometimes 3 waves over the experiment. You can see them in the trajectories. Here, red things is when you slow down. And what was really encouraging at the time was that we were able to demonstrate a saving of 16% in our own vehicles that we could measure. So essentially saying, if you run the algorithm, you save 16%, or you have a 16% more miles per gallon. But what's really interesting too is that if you look at the vehicles straight behind our vehicles, even though they weren't necessarily participating to the experiment, because they had to comply to what the driver in front us was doing, they also saved energy. And of course, the effect goes down as you go further away from the initial vehicle. So this was very encouraging because all in all, it showed that the overall savings we should achieve should be really good. So we built that system, and now it's interesting because if you think of my very first diagram of the air traffic control, where you have a planning layer and a control layer, this is not that different. So ideally, a system like this operates at very high level, queries data in real time. So for us, we bought data from INRIX, and that data produces, so that data looks pretty crappy. I mean, it's that's not their fault. It's just the granularity at which it's produced. So it's something every 500 meters, you have a speed measurements, but you can still see and differentiate with very basic machine learning, what is a bottleneck here. You can see the horizontal, and what is a stop and go wave. And the stop and go wave is what you want to shave if you're trying to save energy. So that type of measurement, which is ingested in real time, enables us to know exactly what the target is for the algorithm. And so the idea is that at a very high level, on the cloud with any infinite compute power, as much as you need, you can compute a speed planning. And a speed plan is essentially the same as what the air traffic management will give to an aircraft. It's like, you're going to fly at this altitude, at that speed, and that defines your arrival time. And based on that, your sequencing is very similar for distributed vehicles. It's like, we're going to give you a speed plan, and at some point, you're going to drive at weird speeds, which are not as fast as you could go, but that's because that's how you smooth traffic. And so there's many ways to formulate this. But one thinking was at the time is that essentially, in order to avoid what's happening often, which is the kind of red thing, which is where you lose all your energy, you would want the blue thing here, which is much better. But because of social norms, and you should not be driving on a freeway at 10 miles an hour, even though it's better for overall traffic, because people are going to be mad at passing you, you have to clip it at maybe 20 miles an hour. And in practice, when you run this on data, that's what it looks like. So essentially, it uses this INRIX data I have shown with kind of a space forecast at the present time, and then time forecast if you have a forecast model on top of it. And then the speed planner defines a target speed, which is this green curve I'm showing here, which is what you push to your vehicle for that. And so that's essentially what you can afford to push over a cell phone network, because cell phone networks have these high latencies and low bandwidth, unreliability. But even if you push a speed plan 15 seconds late or 30 seconds late, the time scales at which the physics of this system operate is a couple minutes. So it's still valid by the time you get it because it's timestamped. So that is something you can reliably do over the cell phone network, even though you don't have a V2V paradigm with a very high bandwidth. And so the idea is that this type of data gets fed to the controller, and then the controller uses it as a target, and then does all the local level conflict avoidance and control. So for that, now we're 2020, and so deep reinforcement learning is very mature. There's lots of libraries we could use. So essentially, we used some reward functions that operated at the system level, in which we could reward vehicles for the energy consumption they would essentially incur in running these algorithms. And it's complicated because for many people who have done reinforcement learning, there's a lot of dark art and magic in finding the proper reward function, so you don't get either absurd solutions where all the vehicles stop because it's better for energy, or other artifact of the optimization, which are not very physical. So we had to add things like variance of the speed and maybe some norm of the acceleration and so on and so forth. And of course, because deep reinforcement learning, at least the way we were using it at the time, is absolutely not certifiable and verifiable. Just that's the way it was, especially if you're using black box deep reinforcement learning to learn the policy. You have to have some form of filter, which were used in our time in the form of the follower stopper is one safety filter. Then we had another safety filter with a clip function, and then the car itself has an anti-collision system on top of it. So there's like 3 layers of safety to go on top of it because it's dangerous. And what it does is actually pretty standard and intuitive. So if you look at the trajectories here, this is an example of a real vehicle trajectory on the test. So it's pretty shaky, and it's normal, right? It's a human driving the orange vehicle. So every once in a while, like at t equals 70, it slows down, and then it speeds up again, and then it slows down. So you can see these things. And the blue vehicle is also a real vehicle. But now it's behind the first vehicle, and you can see a smooth version of the first vehicle. And so all it's doing is it's using the speed target to understand in anticipation how much would you change your speed, and then the low-level controller to make sure that the policy as indicated by the speed planner is executable at the lower level and produces these savings. And so we could already see with single vehicles a lot of savings, and that enabled us to really gain confidence in terms of scaling this up to a larger test, which is when we created the mega vendor test. So we brought about 50 to 70 students to Vanderbilt University, and a bit on Ocean 11 style, created our own org chart, and essentially rented a factory to host everybody. And first question is like, why did we do this in Vanderbilt? Because at the time, Dan Work and John Sprinkle were building this amazing test bed, the I-24 Motion test bed, which is the best instrumented freeway in the world, by putting a bunch of high-resolution video cameras every 500 meters on that stretch of freeway. So this is a multi-million-dollar investment from the state of Tennessee and a variety of other agencies, which Dan Work and John Sprinkle put together, giving us an opportunity to be the first test run on that freeway to demonstrate the technology. What you see now is they are erecting these poles, and this is really a couple months before the experiment. We were really lucky with the timing here that they were building that huge monitoring infrastructure, which we later used to produce the time-space diagrams that were used by the team to build the data. And so we put all the students into our field headquarters, which is this factory or offices we rented at the time. And then the students started mounting radios and all the infrastructure. If we're going to run an experiment with 100 vehicles, you need to build about 120 or 130 hardware, factoring the kind of break things along the way. And then they taught us how to unmount panels in cars. You can see all of us mounting and unmounting things, bypassing the electric system to power our own electronics from the vehicle, and so on and so forth. And essentially, one by one, deployed this into the vehicles that we deployed on the field. We created our own Wi-Fi access points to ship vehicles directly. The the algorithm, so that every day when we would try a new algorithm, we can just Wi-Fi it directly to the vehicle. Vehicle downloads the code, compiles it on the Raspberry Pi we have in the vehicle, and can run the controller. And the Raspberry Pi has nothing particularly glorious. I mean, the electronics is very small. The good news is you don't need a huge computer to run this. It will run a local Raspberry Pi, and then you can just download this every day you want to do a new code. We recruited a lot of drivers. It's interesting that to get 100 people drive at the same time, you probably need to reach out to 700 people. So anywhere from the bus terminal to the airport to the dining halls, we had to offer a lot of money for people to be willing to drive from 6 a.m. to probably 10 a.m. every day. So show up really early so we could catch these first waves. So the drivers would come, they would come to our training facilities, they would be briefed the weekend before, and then every morning before doing the experiment, they would be briefed again just to teach them the basics of safety. Because I mean, they were essentially riding vehicles, running algorithms that we had devised, and they were not professional drivers. We had cashiers, we had people who worked in the insurance business, we had retired teachers, all kinds of professions. So they're not professional test drivers; they're just normal people. So we managed about 150 of them while we were running the experiments, and the type of supervision or the type of instruction we're giving is very simple. It's like, okay, you're driving a Nissan Rogue, so there's a little bit of an onion button here. This is the autopilot button. And your job, if you're a driver for this experiment, is simply to press the automated cruise control button, but just be aware that first, only do this when you're on the freeway. And then if you experience anything that is weird, that's probably normal because it's not your cruise controller. It's actually our algorithms running in the back, and it will show you things which you're not used to. So these 3 bars that tell you the specific intervehicular distance might change on the basis of what we tell you. So if anywhere along the road you're not comfortable, and it gives you target speeds that you're not happy with, you disengage, brake, it will automatically disengage the autopilot. And be aware that you're not running your typical cruise controller, you're running an experimental algorithm. So we give them these QR codes that enable them to drive back and forth on that freeway, so we could achieve the proper concentration of vehicles at a given time, which is what you need in order to manage traffic and smooth it out. We had our own police officer and headquarters security team here to understand and make sure that if something happens, we can intervene in real time. And essentially, we had a total amount of 100 Nissan Rogues that came straight out of the Nissan factory, 5 Toyota RAV4s and 1 Cadillac XT5, each of which running different algorithms or different build of the same algorithms based on the 3-layer cake I showed you earlier, operating possibly at the same time on the freeway. So running the operation is essentially like running an airport or an airline. You release the cars around 5 a.m. in the morning when traffic starts to happen, and then you route them, and then you have a fueling truck, and essentially people run the experiment until traffic dies around mid-afternoon. Then we would, mid-morning. And then in the afternoon, we would run smaller tests with maybe 10 vehicles or 15 vehicles in order to debug what has happened and understanding how we could improve this the next day. So we run this for about 2 weeks, essentially ramping up from 1 vehicle test to 100 vehicle tests on the last day as we turn on the system. So this is a couple pictures from the experiment. You can see Dan Work and John Sprinkle, who really were the 2 heroes who ran that entire facility. This is the Nissan chief engineer, Niels, and then Amaury Ayat from ESTP in France, GFU, and many others running these tests in real time as part of the crew. Most of the vehicles were just 1 driver in it, just doing their driving, but we also had our own crew in some of the vehicles to look in real time about just checking and how things were going. We did run a press conference as we were doing the last day of the experiment, which was really nice because it was an interesting way for the community to find out what we were doing. We're trying to be very stealth initially so that people don't drive differently on that day, but at some point we had a lot of helicopter traffic of TV crews, so we decided to tell the press what we were doing on the last day so they also could be part of it. So to give you a sense of the data we were collecting in addition to everything on our cars, the amazing test bed of Dan Work and John Sprinkle, the I-24 Motion, captures everything there is on the freeway, so it's completely crazy. That data is also complex because you have to track a vehicle from a camera to another, but classical machine learning does that. And so with that data, we were able to build what to this day I believe is still the largest time-space diagram in the world. So I'm showing you a downsampled version here. Each of the dots is a vehicle sampled at probably 1 hertz, even though the camera is about 60 hertz, I think, as a minimum. And the reason why these trajectory crosses, this is across the 4 lanes, so we can also deconflict that. And then the white trajectories are the trajectories of the self-driving vehicles. And then to give you a sense of the scale throughout the day, that's what it looks like. So I'm progressively zooming out so you can appreciate the scale. And also the penetration. You can see there's not that many self-driving vehicle in that thing, and this is the whole day. So it's quite interesting to see that we have to be very soft here. So we did not remove the waves. We improved the waves. We improved the energy consumption of the waves greatly. I'll show you that in a minute. But to remove the wave, you either need a lot more cars or a lot more aggressivity in the way you do it. Imagine a chain of tanks just blocking the freeway in the way the police can do that if they do snail operations. But this is the first time it was done at that scale. So we had to be very careful. And we also had to be very careful not to be noticed, because as soon as people notice you change flow, they try to outsmart you. And then it creates a lot of other feedback loops that we did not model. So that was the idea, was to be stealth enough that we could do some improvement, but not noticeable too much that we would be noticed. And the way you can measure the improvements is by looking at things like variance of velocity acceleration pairs. So a typical pattern of stop and go has an oscillation between fast and slow. And then, of course, if you go from fast to slow, then you decelerate. If you go to slow to fast, you accelerate. So there's a positive acceleration and negative acceleration. And so the idea is that you really want to bring these two closer. And so what we could show is that with the convex hull of the 90th percentile of these acceleration velocity pairs, we could greatly see that diminution, which characterizes itself also in the shifting of the speed distribution in front of an automated vehicle and in the back of an automated vehicle. So to assess the validity of what we're doing, you have to do statistics where the distributions you compute are the distribution of velocities with respect to the position of an AV over all the AVs. And if you do that, for example, what you can see is that if you're 20 meters to 30 meters to the nearest AV, if you're ahead of the AV, there is a pocket of slow moving vehicles, because you can see there's a peak around 7 meters per second. If you're behind of an AV in blue, that peak is much smaller and there's a lot more spread. And that makes perfect intuitive sense, because if you're 20 meters ahead of an AV, that means that you're very close to an AV. That means essentially you've already been stuck in some wave, and therefore the AV can sense you're going slower. But if you're 20 meters behind an AV, that means you're probably trailing the AV, and the AV is smart. It's actually not going as fast as you would want to go because it's smoothing the wave. So in some ways, you can see how you have shifted these pockets of slow speeds, which essentially lead to acceleration and deceleration, to medium speeds where you're just trailing someone. You might be mad at them because they're going slower, but at the end, you're going to slow down less and accelerate less because you're forced to follow that thing. So this is the way we could assess that locally we could save up to 10% in fuel consumption just around the vehicles we were orchestrating, which was really the goal of what we were doing. And of course, we could plot curves showing the decrease of the effect. So the energy consumption goes up again the further away you're from the AV, and that's understandable because there's only as much you can do. You affect the vehicles around you, but the closer you go, the further you go, the less impact you have. So while we were doing this, suddenly the world changed again, and then LLMs came along. And so we were interested to see if as the very early ages of the LLM came along, we could use LLMs to reverse engineer what we had done. So 2016-17, Dan Work and his team had an explicit controller called the follower stopper. That was the first algorithm. Then we came along and worked with them and had a bunch of deep reinforcement learning algorithms, which at that point became black box. So we created an interesting framework called CLEAR. And what we try to do with that framework is see if we could get an early gen LLM narrate to us what we were doing, which is what this movie shows here. I'm going to try to speak over the movie, but I'm going to let you listen to the voice for about 30 seconds and then explain it. Can you hear the voice speaking over here or not?
as
Yes,
indicated
yes.
by
Okay,
number
good.
5 in the ACC cruise underscore state underscore int underscore data. Since the last planned speed in the velocity array, var, indicates a target of around 53.8 miles per hour, I am maintaining a consistent speed close to the leader's pace. Strategy given the close distance, 45 feet.
Okay, so this is this is like black box LLM application to what we're doing. But the point of this is that we essentially give the LLM the variety of accesses. One way is we can show them the reward function, and then it can infer from that reward function why the controller chooses to do this. So it can figure out, oh, he wants to reduce the variance because he sees the variance. And so essentially, it's very interesting because what we wanted to show at that time, and now that whole thing is obsolete because this world is moving too fast. But it was interesting to see that even though the policies we were developing were black boxed, you could actually verbalize them in a way that a human would understand what's happening and why it's happening. And you can see now how we're converging back to the very beginning of my talk about air traffic controllers, because ultimately, if this goes in production, there needs to be a way for the human to understand what's happening if the human is going to feel more comfortable. So going back to this very first picture I'm showing here, maybe now there is actually an interesting thing to be said about a rebirth of what we were trying to do 25 years ago, but for the low altitude airspace. In the high altitude airspace, I think that traffic operates in a very specific manner with humans in charge of air traffic controller sectors, and that's likely not going to change quickly because of the way the industry is set up, the infrastructure is set up. On the other hand, on the ground, the economy of eVTOL, so flying taxis, but okay, essentially electric vertical takeoff and landing aircraft, is going to boom over the next 10 years. And there is no FAA infrastructure comparable to the en route airspace to support it. So regardless of legacy, that paradigm I was showing before, some version of this has got to happen over the next 10 years in the low altitude airspace. There's just no choice because otherwise there's going to be chaos. So one thing we were interested to now look at is, well, now that we have this understanding of how the voice and the maneuvers can be connected, first because we tried to do it and didn't really succeed 25 years ago other than through classical optimization, but now because of the rebirth or the new revolution in the LLM space, maybe with joint embeddings, there is a way to see if we can map encodings of voice, which is available through radio for the low altitude airspace, with very specific maneuvers, either for descriptive purposes and design. And that's something that now, again, in this long after September 11th world, there is a chance to do that. So we've started working on this in the specific context of Airlink, which is this concept we have at Berkeley, where we would like to start connecting the different campuses in the UC system with eVTOL when that becomes a reality. And for that, ADSB provides a really good set of data that we can connect to weather data and that we can connect to radio for which we can listen to frequencies. And so typically, one of the visions we have is as we enable this California Airlink to grow, we would like to also experimentally try to see if we can start moving more towards the digitalization of the air communication in the spirit of later assisting maybe humans in charge of a much larger number of aircraft to coexist in that space. And so for that, we're looking at specific trajectories. This is an example of a flight plan between vertiport or helipad of Richmond Field Station at Berkeley and the Berkeley Space Center, and see how these verbalization could enable multiple aircraft to interact in a way that is at the same time compatible with human language, but also with maneuver design if we were going to do this at scale. And so this is essentially the end of my talk. I wanted to, again, thank the whole group for hosting me today. I was really happy and excited to be here. I want to say hi to Andreas and thank you, Andreas, for the invitation. I guess we are probably short to the end of the hour, but I'm happy to answer a few questions if there's any, or to stop if we have to stop on the hour. I guess I'll let you guys handle that.
Thank you very much, Professor. That was an excellent talk. I'm waiting for questions in the chat. In the meantime, could you explain a little bit the future directions that you presented? What are you planning to do?
Okay, so let me try that. Yeah, so the idea here is that maneuvers are very procedural, and so maneuvers are usually verbalized or could be verbalized very specifically using FA phraseology. And so that is something that can be expressed, and the semantics can be modeled and maybe a higher dimensional space in order to do a mapping between what these commands tell the pilot to do with very specific state space variables in the system, which in the case of ADS-B data include lat, long, speed, altitude, climb rate or decrease rate, and heading, and a few other variables. And if that was the case, then if that mapping could be learned, then this could become the basis of a language to do design over. And obviously, there's going to be a lot of questions raised by that, because if this becomes a synthesis language, then you need certifiability, you need some form of verification tools to run on top of it. We're not even there yet, because we don't really know. This language is very messy, even though there is a phraseology, just like in military English, or like FAA has a very specific set of rules you have to obey. So the first step is really to understand if such a mapping is realistic or not. And we don't have a clear answer to that now, at least for the type of traffic we're considering.
Thank you very much, Professor. I do not see any question in the chat, so I guess we can conclude the talk if there is no question from the audience.
Well, thank you again for the invitation. It's been my honor to be here. And then best wishes for the seminar. It's awesome you're running this seminar online. Thank you.
Thank you very much, Professor.